Hi guys, welcome to 3.1 where we're going to eventually be solving quadratic equations by taking square roots. Now, we have solved quadratic equations by factoring, and now we're going to move on to a type that we can solve by taking square roots. They're called simple quadratic equations. So for instance, an example of a simple quadratic equation is the one we have here, x squared equals 16. Now to solve this equation, it is rather simple because if x squared equals 16, that means if I take the square root of both sides, I should get x by itself. But what we have to remember is that 16 is the square of two different numbers. Not only is 4 squared 16, but also negative 4 squared. So we would have to write x equals plus or minus 4 as solutions to this equation. So there are two solutions, as we're used to seeing with a lot of quadratics. Now, unfortunately, not every number is a perfect square. So before we get into solving, we're going to learn about simplifying radicals, and this should be review from Algebra 1. I'm going to start with the product property of square roots, and in the next video, we're going to do the quotient property. So when solving simple radical equations of the form ax squared plus c equals 0, notice that we don't have a bx term. That's why we can use square roots. So when we're solving equations of this form by taking square roots, we may not always end up with perfect square roots like we did above here. This was perfect because 16 is a perfect square. In these cases, you will need to use the properties of square roots to simplify the solutions. So our learning target is I can use the properties of square roots to express radicals in reduced radical form. Okay, so one thing we're going to learn here is that we're never going to give a rounded answer when we're taking the square root. We're always going to give an exact answer, but it's going to be given as a reduced radical. So we're not plugging anything into our calculators here. So the first property we're talking about is the product property of square roots. Remember, the product means to multiply. So that's our name. In words, it is the square root of a product equals the product of the square roots of the factors. Well, in symbols, it might look a little easier. If we're taking the square root of a times b, I can separate those factors out and take the square root of a and then multiply it by the square root of b. And I can go the other way too. If I have separate numbers under radicals, I can always multiply them together to be under the same radical. So this goes both ways. Well, the reason we use this property is because if we have situations like this example, the square root of 12, 12 is not a perfect square, but I can reduce this by finding a perfect square factor that goes into it. Now, if you do not know your perfect squares, it may be helpful to list a few of them over somewhere on your paper. So I'll just do the first 10 perfect squares. Now, I'm going to find the largest perfect square factor that goes into 12, and I'm looking, 1 goes in 12, of course, but 1 you're never really going to choose because everything is divisible by 1. And 4 goes into 12. That looks like that's going to be the largest perfect square that's going to go into 12. So using the property, I can write this is 4 times 3, right? So that means I can split these into 2 radicals. And I'm going to put the 4 in front because I know the square root of 4 is 2. And then I just have 3 left under the radical. 3 under the radical is completely reduced because 3 doesn't have any perfect square factors. So this 2 times the square root of 3 is reduced radical form. Now, one thing I should mention is that when we are given a problem with the square root already in it, like this, it's asking for the positive square roots. So we don't need to put plus or minus on these. All right, I'm going to go through these 6 examples rather quickly, and we will discuss them more in class tomorrow. So we're going to use the product property of square roots to simplify each radical expression. Remember, the goal is to find a perfect square that goes into the number that's under the radical so that we can take that square root and it can be outside of the radical. So I'm looking at 18, and I'm going to go down my list of perfect squares. Does 4 go into 18? No. Does 9 go into 18? Yes, it actually goes in there 2 times. So I could rewrite the square root of 18 as the square root of 9 times the square root of 2. And the square root of 9 is 3, so that can be a number outside of the radical, and the square root of 2 is still set there. Moving on to B, I have the square root of 75. Going down my list of perfect squares, does 4 go into 75? No. Does 9 go into 75? No. 16? No. 25? Sure does. 25 goes into 75 3 times. So I can take the square root of 25 times the square root of 3. I know the square root of 25 is 5. And so my reduced radical form would be 5 times the square root of 3. All right, letter C, I go to the square root of 48. Now, as I go down my list of perfect squares, I see that 4 goes into 48. So if I start with that, I'm going to have the square root of 4 times the square root of 12. That would give me 2 times the square root of 12. But I run into something. The square root of 12 is also divisible. Well, 12 is also divisible by 4. So I could write this as 2 times the square root of 4 times the square root of 3. And I know the square root of 4 is 2. And then I just have square root of 3. So that equals 4 times the square root of 3 because I can take that 2 times 2. You might have also known, if you kept going through perfect squares, you might have also known that 48 is divisible by 16. It's actually 16 times 3. So I could have figured that out from the beginning and gone straight to 4 times the square root of 3. But I got there. I just had to take a couple extra steps because I could still simplify that radical 12. All right, let's us go to D. I have the positive square root of 52. Going through 52, is 52 divisible by 4? And you can just check this in your calculator, and sure enough, 52 is 4 times 13. So I'm going to write square root of 4 times the square root of 13, and that's 2 rad 13. Now 13 is a pretty big number, so you might think a perfect square goes into it, but it doesn't because the first one is 4. 4 doesn't go into that, and 9 is too big to go into that. Next, I have the square root of 72. Now 72, starting with 4, it actually is divisible by 4. Okay, that's 4 times 18. But I don't want to make the same mistake that I made in letter C and have to reduce my radical twice because 18 also has a perfect square factor. So if I think about that, why don't I go to some larger perfect squares? 9 goes into 72. Man, that even works. I could do 9 times 8 if I wanted to. But 8 even has a perfect square factor of 4. The biggest perfect square that goes into 72 is actually 36. It's 36 times 2. So in a one-step simplification, I could do the square root of 36 times the square root of 2. I can show you the other two. If I did the square root of 4 times the square root of 18, square root of 4 is 2. Then you could simplify 18 as the square root of 9 times the square root of 2, which would be 2 times 3 times the square root of 2. Well, 2 times 3 is 6 times the square root of 2. I could do it that way. If I did 9, I'd do the square root of 9 times the square root of 8, which is 3, and then the square root of 8 is the square root of 4 times the square root of 2, and the square root of 4 is 2, and then I have times the square root of 2, and 3 times 2 is 6 times the square root of 2. So I could have done that any of those ways, but making sure that I get all the way down to the end. My final one using the product property is the square root of 27. Does 4 go into 27? Nope. Does 9 go into 27? Yes, it does. 9 times 3. The square root of 9 is 3, and I'm left with rad 3. All right, that is the product property of square roots. Next video will be our quotient property.